Exoplanets. I know that's something we talk a lot about here on this channel, and for good reason, because they're really exciting. And I think one of the most knowledgeable people about exoplanets is Dr. Jessie Christiansen. I've interviewed her many times in the past, and she is always just a wealth of knowledge. And so here's an interview with Jessie Christiansen. She is an astrophysicist. She works with NASA's Exoplanet Science Institute and at the California Institute of Technology. And she's recently started a podcast where she is interviewing the people who are discovering exoplanets. And so we talk about all of the exoplanets that she's excited about, thinking about right now, a lot of stuff like ripped from the headlines. And so if you want more information from the person who really oversees all of this data coming together, that's Jessie. So here's an interview with Dr. Jessie Christiansen. Jessie, it feels like it's been like merely months since we talked last.
It's good to see you again, Fraser.
Now, last time we talked, you sort of helped give us an update on everything that's happened with JWST, especially in planetary, exoplanetary astronomy. Mm-hmm. But there's like, the news has just been coming fast and furious. And you are I sort of imagine you're sort of sitting at this sort of central repository of all the planetary information. You get to look at every new discovery as they cross your desk and consider each one. So I would love to just know, like, what stuff has happened recently that you find really exciting?
I'm going to start by saying I made myself a sweatshirt that says Exoplanet Queen, and that's when I'm working from home on the couch on the archive. I'm wearing my Exoplanet Queen sweatshirt. So you all need to visualize that now. Because yes, I do get to see all of the cool stuff as it's coming out. So JWST found its first planet, LHS 475b. That's pretty exciting. We just put that in the archive last week. It was a planet that we saw with TESS transiting, but we hadn't confirmed it yet. And then they went and looked at it with JWST, and they saw it, and it's there, so it's confirmed. So JWST has its first planet, which is pretty exciting. And JWST continues to spit out really cool but not actually very promising results. So let me put that in context. One of the things we're really excited about is finding atmospheres on rocky planets around M dwarfs. I probably talked about this last time. And we're really excited about the TRAPPIST-1 system. So we've been looking at the TRAPPIST-1 planets. It's a small, cool red star with 7 rocky planets around it. TRAPPIST-1b, the closest one, doesn't have an atmosphere, and they just reconfirmed this last week by looking at a transmission spectrum. So there's a bunch of different ways we look at atmospheres, but a transmission spectrum is where the planet goes in front of the star, and the starlight goes through the atmosphere and imprints the molecules and atoms on the starlight. So we looked at TRAPPIST-1b again in transmission, still no atmosphere. So TRAPPIST-1b, no atmosphere. TRAPPIST-1c, which is the next one out, also no atmosphere, which is kind of starting to get a little tense because TRAPPIST-1d, which is the third one out, is the first one in the habitable zone. So these 3 planets, D, E, and F, are in the habitable zone. And those are the ones we really want to have atmospheres. So we're still waiting for those results to come out. But so far, it's a little anxiety-inducing that we haven't seen any atmospheres yet. We'd really like
the data haven't been gathered yet? I thought they had been.
So the data are there, but they're not available, and except for the team that's looking at them. So JWST data becomes publicly available a year after it's taken. So the people are still the people who put in the proposal to do this still have the data to themselves for a while to work on it. And there's a whole separate conversation about proprietary periods and whether they're good for science or not. But there's currently a proprietary period, so people can't see the data yet until it's published. So TRAPPIST-1 is still putting out cool stuff.
So TRAPPIST-1, the other world that I think we've all been quite excited about was this possible hycean world, the one with, but for sure carbon dioxide and water vapor, maybe. No,
it turns out. Yeah.
Oh, wait,
so
okay, all right.
This is the cool thing. So K218, it's a sub-Neptune sized planet. It's about 2.6 times the radius of Earth. So it's well above a rocky planet. We don't think it's a rocky planet with a thin atmosphere. And a few years ago, there was this tentative detection of water vapor with HST in the atmosphere of this thing. It's going to be water vapor, not liquid water, just given the pressure in this planet's atmosphere. So at the time, it's really hard to find biosignatures right now, just because of where our technology is and where we think biosignatures are, which is Earth-like planets around sun-like stars. But bigger planets make bigger signals that we can see with our current telescopes. So this group at Oxford, led by Niku Madhusudan, was like, what if this sub-Neptune-sized planet wasn't actually just like a mini Neptune? what if it was an ocean world, so like a rocky core, but like a 50% ocean world that had a really extended hydrogen and helium atmosphere? That might be habitable because at the bottom of that atmosphere, the pressure would be right for liquid water to be at the right temperature for life as we know it. And if that existed, we'd be able to see it because of the deep atmosphere making a big signal. So it was a hypothetical type of planet they came up with to see if there was some way to search for biosignatures, because you need a big signal. So they're like, if we made it have a big atmosphere, it could have a big signal. So then they got JWST data, and they found carbon dioxide, and they found methane, and where they found carbon dioxide and methane kind of disproved the original water. All of these molecules kind of have features very similar to each other, very close to each other. But the better JWST data kind of said it's not water, it's carbon dioxide and methane. And excitingly, for this group at Oxford who are doing this, there was like a little wiggle. Now, it's not a big wiggle. I'm saying little on purpose. And it's not a very statistically significant wiggle. It's a 1 sigma detection. Now, for people who do any kind of statistics, that's barely a detection. So like 1 out of 3 times, that'll go away with more data. That could just be a statistical fluke. The real standards are more like 3 sigma, which will go away 3 out of 1,000 times, or 5 sigma, which will go away like 1 out of 1 billion times, right? If you're trying to claim a detection of something, how significant that detection is really important. So this molecule they found, dimethyl sulfide, DMS, has a 1 sigma detection, so it's not secure. But they looked for it because they were like, what kind of biosignature might exist on this water world, which they're calling hycean worlds? And they came up with this idea that dimethyl sulfide might exist. Because here on Earth, dimethyl sulfide is produced by phytoplankton, which live in our oceans. And if you had an ocean world with much, much, much more water, you could create a much, much bigger dimethyl sulfide signal. So there's a kind of a chain of assumptions to get from, we have a sub-Saturn that we have a sub-Neptune that has methane and carbon dioxide and a wiggle, to we found a habitable hycean world. And it's important to note this is all coming out of one group at Oxford, this whole idea of like hycean worlds that are habitable and looking for biosignatures. So that really needs to be independently verified by other people. And obviously, this is the motto of astronomers everywhere. We need more data. This is always the clarion call of astronomers. Give us more data. So obviously they'll go back and look at it more with JWST to see if this dimethyl sulfide wiggle sharpens up or just goes away. But it created a lot of chatter, right? Because we think a lot about biosignatures, and I'm sure that your viewers think about, like, is oxygen a biosignature? Well, no, because there are geological and geophysical ways to come up with oxygen. Is water a biosignature? Well, we see water elsewhere in the solar system where we haven't seen evidence for life yet. So it's like, what is really evidence of life? What could you look at and be like, there's no other way you could make this? And on Earth, dimethyl sulfide is one of these things. And then recently, like last year or the year before, there was that phosphine detection in Venus, which is still, people are going back and forth on that. Phosphine was kind of a out of nowhere kind of biosignature that people had talked about for 20 years. And dimethyl sulfide, people have been talking about for 20 years, but they're not molecules we're familiar with, right? When we think of life, we're not thinking about dimethyl sulfide and phosphine. So it's these like trace gases that are going to be very, very difficult to detect. Like Venus is right there. Venus is right there, and we still don't know if it has phosphine in the atmosphere, let alone the rest of these planets, which are tens to hundreds to thousands of light years away, where we have like a little spectrum. So it's tough. That's all to say, this is really tough. And I'm excited that people are coming up with ideas for new ways to look for this and new places to look. But I think that the hype, like, it's a biosignature. Well, we don't know yet if it's a biosignature.
And as the queen of exoplanets, you are encouraging your subjects to be positive but skeptical.
That's right. I mean, that's always science, right? Science, yeah. You should be skeptical of everything you read, and you should think about how they did it and why, and if they had an agenda, right? Like this team had an agenda. I'm going to say it. They predicted that water worlds might have this feature. They got a spectrum. They looked, and there's a 1 sigma wiggle, and they were like, hey! And everyone else is like, really?
Yeah. Right. I mean, this is the team that came up with the term hycean world that predicted their existence and gave some of the characteristics that we might expect to see if those things were found. And then lo and behold, one of them was found.
Well, it's we don't even know if it's a hycean world. It's just a sub-Neptune The problem is these planets, we only know their bulk density, right? We know their size and their mass. And there's a lot of degenerate ways to build a planet with that size and that mass, with a very dense core and a very light atmosphere, or an intermediate set of like a small core, a rocky layer, a thin atmosphere. There's all these different knobs you can turn. It's a ternary diagram. There's a triangle with like rock and water and gas. And you can be like anywhere in here and create that density out of these three things. So we don't know if it's an ocean world. It's just, if they existed, they might look like this. But there are lots of other sub-Neptunes as well that we have found. In fact, they're one of the most numerous kinds of planets we found.
And yet there is this gap.
Between sub-Neptunes and super-Earths?
Yeah.
Yeah. Ooh, can we talk about the gap?
Yeah.
Okay. So
whatever you want to. So, yes.
I want to talk about the gap because I just had a paper get accepted that I think might explain the gap, which I'm very excited about. There's this gap in the size distribution of small planets. So when we look at the number of small planets with size, what we see as we go from giant planets to smaller and smaller planets is it goes up. It goes up very sharply. There's many more small planets than big planets. But what we see on this curve is this wiggle, this feature between sub-Neptunes and super-Earths, which are, 1.5 to 2 times the size of Earth. So there's a valley in between. Nature likes to make sub-Neptunes and super-Earths, but doesn't like to make this kind of planet. So this has been a long-standing mystery since it came out of Kepler data 6 or 7 years ago. Why? What's creating this gap? And there are 2 main theories. The first, I should say these are all short period planets. These are all planets very close to their star. This valley exists out to about 40 days. The first theory is called photoevaporation, that you are just so close to your star that the star is like a hairdryer, right? It's just like a hot air just blowing off your upper atmosphere. And if you don't have enough mass to hold on to your atmosphere, then you'll lose it. And that this critical mass is somewhere in this valley, right? Like if you're bigger than that, you can hold on to your atmosphere and stay big. But if you're in this valley, you don't have enough mass to hold on to your atmosphere in the face of this incredibly high radiation from the star, and you lose your atmosphere and you shrink down and become a super-Earth, which we think is a large rocky planet with an atmosphere. So that's theory 1, photoevaporation is the star. Theory 2 is called core-powered mass loss. When planets form, it's a contracting ball of gas and dust, and they can build up, depends whether we're doing top-down or bottom-up formation, but there's a lot of heat involved. Either you're crashing a bunch of rocks together or you're collapsing a big cloud. There's a lot of heat. So young planets are very hot. And in fact, that's how we find young planets, is by the heat that they're putting off. We can search for their emitted light, especially in infrared, because they're very hot. So this heat that they're putting off is radiation that's coming up from the core of the planet. The core of the planet is heating the atmosphere. And it's a similar idea. If you don't have enough mass, then you can't hold on to your atmosphere, and the energy of formation, the heat, just pushes off the upper atmosphere. And it's the same idea. This critical mass is somewhere in this valley. So there's 2 theories, and they've been going back and forth. There's 2 teams that have been writing all these papers for years and years about which one it might be and what the predictions are. The problem is, in the Kepler sample, which is all old stars, there's no way to tell the difference between these 2 theories because they basically have a critical mass and then you get this separation. Where you can tell the difference is young stars, because photoevaporation is supposed to happen in the first 100 million years, right? So if this valley exists and it's caused by photoevaporation, then if you look at stars older than 100 million years, you should see the valley. Core-powered mass loss is supposed to take much longer, more like 1 billion to 2 billion years. So if you look at half a given year, 500 million stars, 500 million-year-old stars, and you see the valley, then it can't be core-powered mass loss. It has to be photoevaporation. Following so far? So the K2 mission looked at 2 clusters called Praesepe and Hyades, which are 600 to 800 million-year-old, 600 to 800 million years old. And so I was like, let's see. Let's look at the sub-Neptunes on this other side of this valley. And what we found was a very, very high rate of sub-Neptunes at stars that are still 600 to 800 million years old, which means it can't be photoevaporation, or they'd have all been gone by now, but that it must be core-powered mass loss. So this is really exciting.
Or some other mechanism.
Or some other mechanism, but the 2 proposals at the moment, they have predicted timescales, and the result is much more consistent with the predicted timescale of core-powered mass loss than photoevaporation. So this is my exciting recent result about the valley, since you brought up the Planet Radius Valley.
But, I mean, compare and contrast this to another couple of planets that came up fairly recently. There was this one that was like made of metal.
Which one was that?
Oh man, I forget the name of the exoplanet specifically. I can give you the one, but it was anyway.
Very high density.
It had like a density of 10 grams per cubic centimeter.
Yes. So rock is about 5. So
rock is
very
about 5.
dense.
Yeah. And there was like 2 of them, but the gist being like, again, how do you get an exoplanet with a density of that much? And then there had to be something exotic that happened to the planet, you know, either a catastrophic collision with another planet that blew off its mantle, or some kind of mass loss from, you know, from the star blowing away its outer material as well.
So this whole category of planets called stripped cores, where we think, given their size, they should have accreted a huge gas atmosphere, right? Like these should be the centers of gas giants. But what we see are these huge dense cores with no atmosphere. So we call them stripped cores. So there's, again, this whole discussion, how does this happen? What are the theories? And they're also often very close to the star, which points to perhaps some star-planet interaction that's happening. But yeah, stripped cores are also really interesting. The reason I care about stripped cores is one of the things I'm most excited about is measuring Eta Earth, which is the frequency of Earth-like planets in the habitable zones of sun-like stars, which tells us directly how many Earth-like planets are there in the galaxy. Now, as I've been talking about, we've actually been detecting a lot of planets closer to the stars than where Earth is. Earth is out here at 1 AU, takes 365 days to go around. We actually have found mostly planets closer to the star than that just because they're easier to find with our techniques. So what we do is the very dangerous thing of extrapolating. We extrapolate from the population of planets at shorter periods and say, if nature loves a power law, if this continues in this way, this would be the number of Earths out here. But if your short period planets are polluted by stripped cores, planets that started much larger but are now small because they're right next to the star, then you're going to overestimate the number of true rocky planets out here because you think you've got heaps of rocky planets here, but they didn't all start rocky. They got stripped. But the ones out here you don't expect to get stripped, so you should just see the true primordial rocky planet population. That's why I care about stripped cores, because they're really, really making Eta Earth a hard calculation right now.
But then let's go the other end of the spectrum. You've got these ultra puff planets.
Yeah, the ones that would like float in a bathtub because they've got a density of much less than water. Those are cool.
Yeah. How do you get that?
So that's got something to do, we think, with the protoplanetary disk that the planet forms from. So when stars and planetary systems form, it's a large, giant molecular cloud that collapses down. And what you get, because of conservation of momentum, is like a pancake that's spinning. Now, that pancake has a lot of different properties depending on how many heavy materials are in the disk, like dust and heavier elements like iron, things that have come out of supernovas and stuff. The dust to gas ratio, how puffy can it be? So there's a few different ideas. One is that they are born from puffy disks, right? The dust to gas ratio in the disk much more favors gas. Then you still need something tricky to get the actual collapse to start. It's harder when you have these puffier disks. Or there's this idea that after planets are formed, there's some kind of internal, like, ohmic radiation or something that's happening to loft the upper atmosphere up and make what you would normally think would be just a normal gas giant like Jupiter or Saturn much less dense. And so we're still trying to work out what this could be, what this internal energy source is that's puffing these planets up. But it's more puffed up than we've been able to figure out yet. Yeah, super puffs. They're so cool.
Yeah. There was one that came out. Tessa just discovered one, and I was sort of looking into the characteristics of it. And I go through this process where, like, I see a new exoplanet crosses my desk, and I kind of go like, nah, I'm not gripped. Like, this isn't thrilling me. I'm going to pass on this story because there's 40 other ones that I need to look at today.
Right.
I don't have time to be excited by all of them, all of the babies the way you do. But
yes.
And so this one sort of it wasn't the lightest planet that had been seen so far. It was like roughly around the same as Saturn, like a little lighter than Saturn, which was fine, good effort planet, but still not as high as it could be. But what kinds of like what is most surprising now? Like, as you're seeing all the stuff that's been confirmed, all of this, but there is this wave of the unconfirmed exoplanets that's sort of coming our way. What do you think is surprising and hidden in that data that hasn't been really confirmed yet, that's going to sort of shift our understanding of the universe?
Right. So one of the cool things about the incoming glut of planets, especially from TESS and then in the future from the European Plato mission, the European Gaia mission, is, for instance, Kepler really focused on one part of parameter space, which was sun-like stars, right? Because the whole point of Kepler was to measure the frequency of Earth-like planets in the habitable zones of sun-like stars. So all of this new data is just stretching us in so many different directions. Like the fact that K2 looked at these young clusters meant we can start mapping out planet formation as a function of age. The fact that TESS is looking at so many stars that we can characterize really well means we can map out planets as a function of metallicity of the host star. And I'm interested in the chemical abundance of the host star. So for instance, different stars have different chemical makeups, different amounts of oxygen and carbon and nitrogen, all of these elements. And I'm really interested to know if the chemical abundance profile of a given star determines what kind of planetary system it makes. And we're finally actually getting to the point where we could do this because TESS has looked at so many stars that we have high-resolution spectroscopic data on from the ground. There's a lot of large-scale spectroscopic surveys from the ground, like Apogee and Lamoste in China and Galar in Australia. So there's these big surveys where you've got really, really exquisite abundance amounts from these stars. So you can start to say, like, okay, do stars with a really high silicon ratio make rocky planets? Or if you have a really metal poor star, do you not make rocky planets? This is the next thing I'm really excited about, is digging into what different types of stars make different types of planets on a much more granular level than just big stars make big planets, but not a lot of small planets, and small stars make lots of small planets, which is kind of where we're at the moment with our demographics. I really care about demographics, which is the populations of planets, because if you think about the whole galaxy, we're only ever going to be able to search like this much. But the galaxy's huge. But if we can do demographics, then we can actually extrapolate and be like, so the galaxy has 10 billion Earth-like planets. That's what gets me excited. So yeah, chemical abundance profiles.
So do you think we'll get to a point where you could predict the type of planetary system that should be around a star purely on the chemical, the metallicity of the star?
So that's a really, really major goal of NASA right now because of Habitable Worlds Observatory. So NASA's next big flagship mission that we're going to spend the next 20 years building is called the Habitable Worlds Observatory, which is going to do what the name says on the box. We want to look for habitable worlds, Earth-like planets in the habitable zones of sun-like stars. But it's a direct imaging mission, which means it's one of the missions where you have to block out the light from the star and look around the blocked out light for planets. It's very difficult to do, and you can really only do it for the very most nearby stars where they're close enough that the separation between the star and planet is big enough. So we're not going to get a lot of shots at this. We're probably going to be able to look at 100 stars, which sounds bonkers, right? Kepler looked at 200,000 stars. TESS is looking at tens of millions of stars, and we're going to spend some number of $1 billion to look at 100 stars. So we need to know that those are the best 100 stars we could possibly look at for Earth-like planets. They have to have the highest probability of having an Earth-like planet in the habitable zone. Because if we look at 100 stars and we don't find one with a mumble $1 billion mission, that's not going to look great. So it's super important right now to do exactly what you're saying, to be able to predict from what we do know about a star and anything about its system, what the probability of it having an Earth-like planet is.
That doesn't even sound like enough of a guarantee to me. It sounds like with Plato, with other planet hunting telescopes, especially some of the ground-based observatories, the hope is that you already have those candidates lined up, and now it's a matter of observing them to characterize the atmosphere. I mean, to blindly look at stars that you think might have a planet and you're like, oh, nope. That seems like by 2035, 2045, we must have the candidates in hand by that point.
So part of the justification for this mission is actually none of the things you mentioned are sensitive to Earth-like planets in the habitable zones of sun-like stars. Like Plato will not do it. Plato will go back to the Kepler field and potentially, maybe, if the stars align, literally and figuratively, help us with some of the Kepler candidates that we already know. One of the problems is that the Kepler candidates in the habitable zone are very unreliable. So we compare the properties of the signal to the properties of the noise in the data. And what we want to see, obviously, is that the signal is very different from the noise. And many of these long period small Kepler candidates, the signal and the noise are almost indistinguishable. So you might have heard of Kepler 452b, which was like Kepler's big success, which is like a potentially rocky planet. It's about 1.5 to 1.6 times the size of the Earth. in the habitable zone of a sun-like star. It was the only one we found, and it might not be real because the signal is very similar to the noise. So it's unreliable. So Plato will go back and look at that field and potentially help us characterize some of those. Radial velocity doesn't have a clear path forward to Earth-like planets and habitable zones of sun-like stars. They're getting more and more precise every year, but this current generation of instruments is down to 30 meters a second, 30 centimeters a second, and we need to get to 8 centimeters a second to see Earth-like planets. So we're still a factor of 4 or 5 away. Direct imaging is the way to do this, is the way to find these planets. It's just really hard and really expensive.
Right. And so there doesn't feel, because it feels like that's the way that you get you have something, the finder scope that is analyzing the 100,000 stars within 100 light years of us or whatever. You identify all the ones that have Earth-sized worlds orbiting around sun-like stars within the habitable zone. You may not have any data, but at least you know it's there. And then you bring the big guns to bear on this beautiful candidate and see what you can find.
Yeah, ideally, in a perfect world.
We don't have that finder. Yes, we don't have that finder scope.
We don't have the finder scope, unfortunately. Yeah. It's just really difficult to do this. And the problem, the other thing I'll say is that transit and even radial velocity rely on an alignment that eliminates many nearby stars. Like if you think about the fact that Earth has a 1 in 200 chance of transiting if it's around a nearby star, that means only one of the 200 nearby stars would have an Earth transit around it. So transit is not a good way to do it. Radial velocity doesn't have as strong a dependence, but if you get close to a face on orbit instead of an edge on orbit, it doesn't work. You can't see. So this 8 centimeters a second that we're aiming for is if you have a perfectly aligned orbit and the maximum velocity is coming towards you and away from you. So the thing about direct imaging, it doesn't matter, right? Because direct imaging is you can see it on the sky. If you get very unlucky, which we have done with some systems, the planet is either directly behind or directly in front of the star, and then it's hard to see. But the idea of the mission will be to survey these stars over a number of years to watch to see planets come and go.
Can astrometry get you there?
So Gaia, for instance, is the European astrometry mission. It's only really sensitive to giant planets. The next generation of astrometry missions, which is probably 20 years away, may get us down, but even Gaia is only giant planets, not rocky planets.
Yeah. Yeah, it feels to me, I mean, there was a proposal by John Mather, of course, who was behind Webb and other things, to launch a sunshade and use that, starshade that could work with ground-based observatories. Mm-hmm. And it feels to me like it's going to be really tricky to proceed without having that list of candidates. And it's funny, here we are in 2023, and we still have no Earth-like worlds orbiting sun-like stars.
And you use the word funny. It's not very funny for me. It's very frustrating because I've spent my entire career trying to do this, and we still don't have one.
Yeah, and Kepler was the way.
Kepler was the way, and we didn't quite get there. We were so close.
Yeah. Yeah.
Still breaks my heart.
Would a Kepler, I know you're not in charge, but I would put you in charge, but, would a retake on Kepler get us there? Could there be a super Kepler?
So there is actually a Chinese mission called Earth 2.0, which is basically a redo of Kepler. They want to build, instead of one monolithic telescope, which is what Kepler was, it will be more like Plato or TESS, which are arrays of smaller telescopes just because they're cheaper and you can get more of them. So there's this Earth 2.0 mission, which is actually planning to go back to the Kepler field and just sit on the Kepler field, which is actually what we would really like Plato to do, but they're the European mission and they have their own science goals, which is fine. They're allowed to have their own science goals. But the Earth 2.0 mission is just going to go back to the Kepler field and look there. So if that flies and achieves the precision they're hoping to get, we may be able to confirm some of these unreliable candidates. Depends how kind nature is. We don't know whether Eta Earth is high or low. It might be 5%, it might be 50%. If it's 5%, that's not great because we're going to look at 100 stars and find 5 Earths.
Right. Oh, and if it is high, then every system you look at is going to have something, we have 3 of them, right? In the solar system, we have 3 planets in the habitable zone.
We have 3 Earth-like planets.
Yeah. In the habitable zone. Mm-hmm. They just don't happen to all be habitable.
Yes, it's an important distinction, especially when we're announcing all of these like habitable zone exoplanets. It's like, yeah, but not actually habitable.
Right. And I think that's vital, right? That when you look at it mathematically, yeah, Venus is in the habitable zone, Mars is in the habitable zone, and they suck. And it's, when you actually look at them, and so definitely when we see these planets in other systems, you're going to want to observe them. And then this is where we get. So, I mean, the question that I feel like I've asked you this every time, and because I think the answer is evolving, is, are we normal?
Yeah, no, it is a good question. So our inner solar system out to about Earth, which is what we know pretty well, our inner solar system is normal-ish. So one of the things we've seen is that systems with multiple small planets close to the star like to make planets of the same size. It's peas in a pod theorem. It's really kind of cool. So if you put 4 planets right next to a star, if you draw those statistically from the exoplanet population, they should be all different sizes because we have all different size exoplanets. But what we see is that those 4 planets are often, most of the time, very similar sizes. So the fact that we have 4 small rocky planets as our inner half of our solar system, that's pretty normal. It seems like most gas giants occur between 3 to 10 AU, and we have one at 5 AU and one at 10 AU. So that's fine. That's good. What doesn't seem normal about us is, I mentioned previously, sub-Neptunes are one of the most common types of planets we've seen. So between sub-Neptunes and super-Earths, some very large number, like more than 80% of the planets we found are sub-Neptunes or super-Earths. And we don't have one of those. Is that weird? We have 8 planets that sample this large range from Mercury to Jupiter, but we don't have a super-Earth. We've got a big gap between the rocky planets and the ice giants.
And we deserve them.
And we need a super Earth or a sub-Neptune.
It's funny, like whenever we talk about some of these super Earths or mini Neptunes, we talk about how the mass is 1.8 times Earth or twice the Earth or whatever, and the radius is larger. People will go like, oh, well, no civilization could ever get off that world because the gravity is going to be 10 times what they have on Earth. And actually, it's not that much. Some of these ones would only be like 1.1 G. Like you could walk around on a super Earth. And
some of them.
Some of them, yes.
Yeah.
And you wouldn't be trapped that in fact you would just have more room to breathe. It would just be a bigger planet. And depending on the density of the world, that just because you increase the radius and the mass of the planet doesn't necessarily mean that you get double the gravity. You may only get 1.5 or 1.4 the gravity. So
yeah. Especially if you can have a much deeper rock or a water ocean or something. You can really dial all of these knobs to get a surface gravity that you want for a given size and mass.
Yeah. Now, at this point, I hope people are listening to this and they're like, wow, I really like the things that Jessie has to say. How can I hear more from Jessie on a regular basis? And, although I interviewed her many times, you have a podcast where you are interviewing other people. So people want to hear about planets and hear more information from Jessie. Let's talk about your podcast.
Yeah, so we just have this new podcast. It's out of Caltech IPAC. IPAC is the Data and Science Analysis Center on the Caltech campus where I work, which houses the NASA Exoplanet Science Institute, which I'm the lead scientist of the NASA Exoplanet Archive. So we have a new podcast. It's also a web series if you want to see my face, but you could just listen, called Explore Exoplanets, The Discoverers. So what I'm doing in season 1 of this show is interviewing people who have discovered new planets. Because we always get asked the same questions, right? Like, what did it feel like? And what do you think about it? And which one's your favorite? And so I wanted to collect a bunch of people and, obviously an excuse to interview some of my favorite colleagues about their discovery, right? Where were they in their career? Did they ever think they'd find an exoplanet? How did they find it? What did they find? So that's like the first half of the segment is just, getting to know them and their planet. The second half is kind of fun. What I do is I ask them for their favorite fictional planet, and we talk about why it's their favorite fictional planet. Did they love Star Wars as a kid? Did they feel this way about this book series as an adult? And then I go into the Exoplanet archive and I find the closest real-world analog, and we talk about that planet and the closest thing we found. So that's the second half is really this like deep dive into people's loves and if we found anything like that in real life, because people always enjoy that aspect too. So each interview has 2 halves, the first half about the planet they found and the second half about their favorite fictional planet. And we've done 8 episodes so far. The second one has just come out as we're talking now. It's called Explore Exoplanets, The Discoverers. It's on Apple Podcasts, Google Play, your favorite podcast catcher. And it's also on YouTube on our Explore Astro YouTube channel. So the episodes will come out every 2 weeks. They're only about 10 minutes, but they're a lot of fun. I've been enjoying it so far.
And what are some of the science fiction planets that have come up so far?
Sure. So the first episode, actually, it's the original, the OG science fictional planet that appeared in the first movie that had an exoplanet in it. So Forbidden Planet is a film from the 50s, and it's the first film that has a fictional planet in it, and the planet is Altair 4. So we talk a little bit about Altair 4 and what we know about it, and then we find this Kepler planet that has a lot of similar properties. But I just love that it was a total coincidence that it turned out this way, but our first episode is the OG science fictional planet, Altair 4. And yeah, we've talked about a bunch of other planets since then too.
And so, like, if mine was Vulcan, that would be fine. It just has to be orbiting a red dwarf star, right? Like, I'm sure that's like what it always has to be. That's
have we talked about Vulcan before?
No, I don't know. Have we?
Because we found Vulcan and then we lost it.
At Epsilon Eridani, yeah.
Yes, yeah. So in Star Trek, the planet Vulcan is orbiting the star Epsilon Eridani, and in real life, there's a star Epsilon Eridani in a triple star system, and we found a planet around it. It was a giant planet, not a rocky planet like Spock's original homeworld is portrayed, but we found a planet around Epsilon Eridani, and I was so excited. This was like my favorite science fictional exoplanet fact for many years. And then my colleague Jen Burt, who is actually my second interview on the show, went and killed it. She got more data and showed that it's not there. And I'm just like, Jen, that was the best. We found Vulcan and then we lost it again.
And then someone did that with Bernard Star too.
Yes, that was another good one.
Yeah. And Alpha Centauri. Like,
Alpha Centauri.
Yeah, we can't. This is why we can't have nice things.
Yeah, and that one I always remember because it was our Christmas present, right? Like, that came out on Christmas Eve, that Alpha Centauri B had a rocky planet around it. And it was just like, what? And that was like 10 years ago, and I still remember learning this because it's the closest star system to us, and for it to have rocky planets was just so exciting. And then they call it the ghost in the noise, the ghost in the time series. It's gone. It was just a window effect.
Yeah. What are you obsessed with right now?
What am I obsessed with right now? I'm kind of obsessed with Habitable Worlds Observatory, which we've just been talking about, which is this NASA's next big idea to find Earth-like things. I'm really obsessed with doing demographics with K2, which was the sequel to the Kepler mission when Kepler wasn't going to be able to keep pointing at its original field. And I'm really obsessed with Roman, the Nancy Grace Roman Space Telescope, which is the next thing that NASA's going to fly in 2.5 years from now. No later than 2.5 years from now is how they word it, the wiggle room. So Nancy Grace Roman, it's a 2.5 meter telescope like Hubble, but a much wider field of view. And why it's exciting is it's going to do a microlensing survey of the bulge, which is another way of finding planets. And it might be sensitive to Earth-like planets in the habitable zones of sun-like stars, but around very distant stars. So it doesn't really help us with habitable worlds, but may help us with the statistics. All of those things.
I'm doing an interview tomorrow about the coronagraph on Roman.
Oh, yay!
So, yeah, so our obsessions are lining up perfectly here.
Great. Who are you talking to? Now I'm curious. It's okay.
Vanessa Bailey.
Yeah. I was going to say, if you're not talking to Vanessa, make sure you talk to Vanessa. She's good people and also the world expert on the Roman CGI. Yes.
Yeah. And this is like, I'm obsessed with coronagraphs right now. And, and so I just did an interview about an interferometer, about doing like a far infrared interferometer. And when you run an interferometer with multiple telescopes, you get another technique that you can use called nulling. And so there's another way that you can block the light of the star that doesn't require a coronagraph, doesn't require a star shield.
Right. Have you interviewed anyone from the LIFE mission, the European mission called LIFE?
No, not yet.
Okay. That's super cool. That's a really cool idea. It's a space-based interferometer to search.
Yeah, I mean, like
planets.
just the fact that there are no space-based interferometers that ever flew. There was the space interferometer mission that got canceled, and then there was the habitable planet finder, and that got canceled. Yeah. And so just nobody has had the guts and the budget to send one of these things to space. And doing a far infrared makes a lot of sense just because the wavelengths are more forgiving than try to do something in the visible. And so I'd love the idea of seeing one of these fly and then just move your way up the electromagnetic spectrum
Sure.
with more and more
What's also an
complexity.
amazing visual, right? Formation flying telescopes in
Yeah.
space. It's just so cool, right?
Yeah.
That's the future. That's awesome.
Or like some kind of spider web that has telescopes at all the ends of all the nodes, and it's, you know, it's flying like some kind of giant, I don't know, spider web in space would be fine too.
That's very Doctor Who, spider web in space.
Right. Yeah, exactly. Well, Jessie, always a pleasure. Your podcast again, in case people are looking for it.
It's called Explore Exoplanets, The Discoverers.
Wonderful. And I look forward to talking to you again about more exoplanets. Whenever something new turns up, let me know.
Always happy to chat. Thanks, Fraser.
All right. Thanks, Jessie. I'm going to talk about my thoughts about exoplanets in a second, but first, I'd like to thank our patrons. Thanks to Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew Gross, and Josh Schultz, who support us at the Master of the Universe level, and all our other supporters on Patreon. It really does feel like an exciting time in exoplanetary research at this point. I mean, there are way too many planets for us to cover them all, and now we're having to think about them in bulk. And yet, the loss of the Kepler's reaction wheels is like this shadow that hangs over this whole process. Like that was going to be the machine that was going to get us those other Earths orbiting around sun-like stars in the habitable zone. And because Kepler's reaction wheels failed, and, they went on to discover plenty of cool planets around red dwarf stars, but there's this gap in our knowledge about the part that, I think we all want to find, that other Earth. And it's going to be tough as we move forward and as the next generation of telescopes come online, designed to make those follow-on observations. We won't have the candidates. And so I think, there's going to be a real demand for clever ideas, ways to push existing instruments and telescopes to the next level so that they can find those candidates, so that when the Habitable Worlds Observatory comes online in 2040, it'll have targets to look at. And that's going to be really important. I just want to give you another encouragement to go and follow Jessie's work. Her new podcast is terrific. Interviews with these exoplanetary astronomers. You can really see the details that they're working on, the discoveries they're making, the techniques they're using, and to see colleagues talking to each other. Like, this is something that we don't get a lot of out there in media, and I think you're going to find this really entertaining. So subscribe to her podcast if you like to listen to podcasts, or we'll put a link to the YouTube channels. You can go there as well, and you can find more information over time. All right. Thanks a lot. I hope you enjoyed this, and we'll see you next time.